this short little presentation to give you a feel for some of the work we do here at the University of Minnesota with respect to building what are called small satellites called CubeSats. So it's kind of a tutorial of the sorts. And then I'll share a little bit about, actually, I'm not sharing my screen, so you're not seeing what I'm saying. There, all right. And can everyone see that and hear me? All right, so think of this as a tutorial of sorts as to what CubeSats are, what they're all about. And then I'll tell you a little bit about the work we do here at the University of Minnesota with building and flying CubeSats. And then at the booth downstairs, you will find our group here that is building CubeSats, and you can talk to the students there and they can tell you a little bit about what they're doing. So again, more of a tutorial and then a little bit of the things that we're doing here at the University of Minnesota with respect to CubeSats. All right. So by the way, for those that don't know me, I am a faculty member here in the Aerospace Engineering Department of the University of Minnesota. I'm also the director of the Minnesota Space Grant. James and I work together to run the space grant. So CubeSats. So CubeSats are a class of satellites that came into being, I would say somewhere around the early 2000s when people had the idea and started putting it together. And basically what they are, as their name implies, they're spacecraft that you build by putting together blocks of units called 1 unit cubes, which are the things shown here. They're 10 centimeter by 10 centimeter by 10 centimeter cubes. And there's a lot of hardware there you can buy off the shelf, and you can put together one of these things and you can stack them together, very much like Lego blocks, all right? And the nice thing about CubeSats is what they've done is they've allowed scientists, engineers, whatever who want to do some sort of science, they could go ahead and build these CubeSats rather inexpensively in quotes, relative to what it costs to build real big satellites. And then they don't have to worry about integrating this with some large spacecraft. If you build a CubeSat and you follow the standards for it, then you could pretty much shove them into any spacecraft that has space on them, and they'll hitch a ride up to orbit, right? So that's the whole idea. And they've become, I mean, they kind of started out as toys, but now they're actually being used for serious research. They're being used for serious missions, and I'll show some of those to you. All kinds of things, commercial, there are people making money off of CubeSats now, and I'll show some examples of that, but there's a lot of educational projects, there's a lot of scientific, there's a lot of technology demonstration that's being done. And again, the idea is you take these these 10 by 10 by 10 centimeter blocks, and you put them together as need be. So you'll hear folks talk about a 1U CubeSat. What they're talking about is a 1 unit 10 by 10 by 10 centimeter. When they say 3U, it's 3 of these things put together, and people stack all kinds of different sizes of them. The largest one that I've heard of is a 27U satellite, which is 27 of these blocks put together, right? So that's the basic idea of CubeSats. Now, let me show you a video here. This is a CubeSat being launched. So on the International Space Station, there is a launcher. There's a company called NanoRacks, which if you want to get something to orbit, you contract with them and they'll arrange to get your CubeSat up to the International Space Station and inject it out of there to orbit. And if this video works, you'll see a 3U CubeSat being chucked out of the International Space Station. I have no idea what CubeSat that is, but it's going to go out and do science or something, all right? So the bottom line is these CubeSats have made it very easy for people to get things launched, put into low Earth orbit, okay? So this is a picture here of a pair of CubeSats just having been ejected out of the International Space Station. And what's significant about these CubeSats is this. So a couple of years ago, it's been about 10 years or so, but Carl, you might know better. I don't know if you do any work with Planet Lab images?
I've looked at it a little bit.
Okay.
I haven't really worked with them yet, but
all right.
I'm aware.
So that is a CubeSat. It's a 3U CubeSat called a Dove. And the company that launches them is called Planet Labs. They've gone through different changes of names. It's a company based in San Francisco. And they have about, last time I checked, they had over 100 of these CubeSats in orbit. And they're constantly taking pictures of Earth, and think of them as the Google Maps from space version. So if you go to their website, and if you're in an academic institution, there is actually an easy way to get their pictures for free. And imagery of the Earth from space, and it's all done using these small 3U CubeSats called the Dove. The neat thing about these, Planet Labs, is they actually commission artists to put some really nice, funky abstract art on their CubeSats before they launch them. But just an aside thing. And if I could, so these are the type of images that are coming down from the Doves, right? So this is, I think it's somewhere in Indonesia, was a picture of a volcano. And folks that study this kind of stuff, and I'm pointing to Carl because I think you do that kind of work, you could get real-time imagery of things evolving on Earth, and there's all kinds of cool science that can be done. So CubeSats they've emerged, they came out as a curiosity that people that like building things were playing around with, but now people are actually making money off of them, all right? So Planet Labs is a good example of that. NASA is completely sold on CubeSats, so there's all kinds of missions that are being planned. And here's an example of a 1U CubeSat, so you can see how big it is. All of the solar panels for generating power. That looks very much like a tape measure, and it probably is, because the interesting thing about CubeSats you're going to see is that they use a lot of off-the-shelf hardware and used in a way you would never think about it. So for example, one of the CubeSats we're building, we use these tape measures as springs for controlling the deflection of solar panels. Pretty interesting, but in this case, I think they're using it as an antenna. So this is a 1U CubeSat, an example. It's kind of small, you can carry it in your hand, lightweight. And NASA has a whole set of missions on the book planned that are going to be based on CubeSats. This chart is a little bit dated because that says 2019. That's going to go out on, I guess, the first Artemis mission. It's going to go to the CubeSats that's hitching a ride on it. However, Marco, or a pair of CubeSats called Marco A and B, that actually made history back in 2018. They're the first CubeSats to be used in deep space, and they ended up going around and actually orbited around Mars, right? So that's the pair of them somewhere, I'm guessing JPL, while they're being put together. And these are a pair of 6Us, right? So it's, if you look at it, there's 6 of these blocks put together that make the Marcos. And I love this picture. It's a picture Marco B took on November 26, 2018, while it was in orbit around Mars. So you can kind of see part of its solar panel there, and it's taking a picture, and that's Mars right there. So they've stopped being toys, and now they're actually serious research spacecraft. I put inexpensive in quotes because they are inexpensive compared to other spacecraft. But if you look to build a 1U CubeSat from scratch and all the way to launching it, it's probably going to be a little over 100,000, between 100 and 200,000. So, and you winced, but that's inexpensive in spacecraft lingo. So, all right. So it's a cheap way to get yourself to space. The company Nanorex, if you give them a 1U CubeSat, they'll charge you $85,000 to get it to orbit. So so it's become inexpensive. And yes, again, folks that are not comfortable or familiar with aerospace costs would say that is an expensive thing, but that's a cheap launch opportunity.
So it's $100,000 to put it together, and then another 85.
Yes. Now, one of the nice things about being in an educational institution or a nonprofit, NASA has a program called CSLI, the CubeSat Launch Initiative. If you have a CubeSat built, and you could convince them that it's science or educational worthy, they will get it to orbit to you for free. So that's something to keep in mind. So you don't have to pay the launch costs, but if you're an independent person trying to make money or trying to do business, you're going to have to pay someone to get it up to orbit for you. All right, so with that, what I want to talk about are 3 CubeSats. One that we built and put in orbit in 2019 called Socrates. and then 2 more that are in the works right now that we're building. And you'll see an engineering unit of Socrates down at the display down there. And then you'll talk to the students. They'll tell you a little bit about the other 2 that we're building. So Socrates, an acronym for Signal of Opportunity, CubeSat, Ranging and Timing Experiments. That's a mouthful. What does it mean? It was a CubeSat that was going to fly. I don't know how easy it is to see, but if you see that little top part of it there, that's a X-ray spectrometer. And it was an X-ray spectrometer that was designed to be able to look at X-rays being generated by pulsars, stars that have died off, basically burned off all their fuel, and they're generating X-rays. And there's a lot of work going on, a lot of corners. That's part of my research, but it's also research that's happening at NASA, it's happening at DARPA. It's the idea of being able to use these pulsars as if though they were like GPS satellites. So it's a way to navigate in deep space without having to use man-made facilities. So basically using pulsars as if though they are lighthouses in deep space. So it was just to try to test out that detector that we put together here. So it was launched in 2019. And if I could advance my slide, for some reason it's not going forward. Yes, it is. Okay. So the idea was going to go in orbit. It was going to, it had 5, the whole mission had 5 steps. It's going to get launched, get put in the orbit. It would start up, and then it would start pointing at the pulsar and the Crab Nebula, and just try to collect data from it and see if our detector worked. And then downlink the data. That is Socrates, not complete, but in the process of being built up in our labs here in Shepherd Hall. And I was telling you that you use creative things. So if you see these 2 things here, those are the solar panels that are going to power it. So once they got to orbit, they would deploy out and point at the sun, and that's the way we charge the batteries. And the springs we're using for that are basically tape measure at our. So they actually work on a wonderful spring. So that's what they were used for. But anyway, that's Socrates there in the process of being built. That is Socrates leaving the International Space Station, and I think it was 2020. Anyway, unfortunately, like most CubeSats, or like many CubeSats, Socrates for some reason decided to die on orbit and not talk back to us. So we didn't give up, and we're building 2 more now. So the next CubeSat that's in the works is called EXACT. A different acronym, same mission. So it's going to be the same. It's going to go into orbit, and it's going to stare at the Crab Nebula and try to read off it. However, this time around, the X-ray spectrometer that's going to be flying on EXACT was actually designed by not our team, not my team, but this is a collaborative project I'm doing with Professor Lindsay Gleesner in the physics department. And she's going to use the same detector to look at the sun and start do solar physics work with it. So that's a detector that's being designed by her and our collaborators at Montana State University together. So it's going to be I think it's going to be a better and more refined detector than the one we had the first time around. So the same detector, it's going to be used for looking at pulsars, but it's also going to be used for looking at the sun. So EXACT is going to be a mission. It's going to be a 3U CubeSat, very similar to Socrates. That's going to be looking at the Crab Nebula, while the sister CubeSat, it's a perfect twin. Well, I shouldn't say perfect. It's very similar. Twin to EXACT is going to be called IMPRESS, another acronym, which also rapid energetic solar spectrometer. So again, this is Lindsay's. She's the PI on this one. And it's going to be looking at the sun to understand the physics behind solar flares and coronal mass ejections and things like that. So we're building 2 of them. We are on hook to deliver them to, well, EXACT is to be delivered to the Air Force, and IMPRESS is going to be delivered to the NSF. That's going to use the NASA CSLI to launch it. They're both due next summer, not this summer, summer of 2023. So we're going to be up to our ears building them this summer. So anyway, and if you're interested, talk to me, talk to the students downstairs. We could, if you want to learn about CubeSats and how to build them, then once in a while we do take people into our labs for the summers to help us build them. So right, my laptop's about to die. All right. So if you want to learn more, visit our website. The URL is just smallsatumn.edu. And you'll find about the different projects, different CubeSats that we're building. These are the two, but there are others that we're building as well. And while I open the floor for questions, I will share this time-lapse photography, show a video showing the assembly of Socrates a couple of years ago in the clean room in that building here. So with that, I'll stop. And if folks have questions about CubeSats, we'll be more than happy to answer them for the next 10 minutes. Yes.
What is the lifespan of these CubeSats?
Okay, so it depends on what kind of an orbit they go into and what kind of mission they're doing. In the case of both Socrates and EXACT and IMPRESS CubeSats we're building, they're going to be in a 400-kilometer orbit. They have fairly large surface areas, so they're going to come down fast. So the lifetime, at least now we're predicting for IMPRESS and Socrates, are going to go up at a time when the solar activity is pretty high. So their lifetime is going to be about 6 months. They're going to re-enter the Earth's atmosphere and burn up after 6 months. Yes.
What is the retrieval process once you're done your flight? Like, do you have to get it yourself, or do you like have someone else return it to you, or do you just leave
They're
it?
going to come in the atmosphere and burn up, and we're never going to see them again. So they're going to be a shooting star at night somewhere. So yeah, so the data is going to be they're going to have comm radios on board that are going to be sending out. You're going to be talking to them continuously. So while they're on orbit collecting mission, we're going to be getting the data from them via our radio data link. And that's picking up anyway. Yes. Go ahead. Sorry.
What was Socrates' mission? What was the data that he was collecting?
It's good. That's Socrates is going more or less going to be identical to the CubeSat I said EXACT, and it's going to be looking at the pulsar in the Crab Nebula, and it was going to get the X-ray data coming from it. The key thing we wanted from it, it was going to, every time it saw an X-ray photon from the Crab Nebula, it would put a time tag saying, I received this at this time, and would save it, and that data would have been sent down to us. And from that, we would have been able to figure out how well the spectrometer worked and whether or not we could use these pulsar signals for navigation. So that's what Socrates was supposed to do. EXACT is going to be doing the exact same thing. Okay, I'll go this way. So Jonas, and then I'll.
Okay. So I guess you cannot really point the CubeSat at a particular target. So is the detector such that it recognizes from where the X-rays are coming?
Okay, so the answer, yes, we do. We are going to point it. It's going to have a control system on board for pointing it where we want to point it. And that's why and the reason we picked the pulsar and the Crab Nebula, that's one of the most energetic ones. So it's going to be bright to see. So yes, we are going to point it, but when it comes to, if your question is what happens when you're doing navigation, like later on, the whole idea of doing navigation with pulsars, how do you tell the difference between an X-ray photon from pulsar 1 versus pulsar 2? And that's, yeah. So that's where the algorithms come in. We have estimators aboard, which are actually their data association filters. So they're going to say, what are all the possible pulsars I could have seen? What is the probability of me seeing a photon from this guy? And it starts building up probabilities. And then once it gets them, that's the way it's going to go. Yes. So that's one of the disadvantages of using natural signals, right? If this was a man-made design signal, you'd have identifiers on each one of them. In this case, we don't. So you have to put together algorithms to do that. But yeah, it's a data association filter that tries to match photons from each of the pulsars to the ones we receive.
Do you have little jets then in order to change its orientation?
So right now we're right at the point of almost deciding which way to go, but they're going to be reaction wheels. So they're going to be momentum wheels that spin up to point them. Interesting. I'm going to go around like this in a circle. So, right.
Are there any future CubeSat missions coming onto the radar, and are any of them deep space?
Here at the U of M or at NASA or other
Oh,
places?
no, just here at the U of M.
So none of ours are going to be deep space, right? They're going to
No,
be.
I understand that. Is there anything in the future?
There's in the future, and they're all going to be, no, not deep space. They're all going to be low Earth orbit missions. There's another mission that we're working with the Air Force on. In that case, we're deliberately going to be deorbiting CubeSats to burn them up in the atmosphere. So we're not getting very far away from Earth. All right, so
Are you guys looking at waste statistics or anything when you're choosing the materials, if it's coming down and burning up? What's the thought process behind that?
All right, so I'll answer that question in the following way. So when you build CubeSats and you're going to give it to someone to launch it for you, one of the things they make sure is you have to have, you're only allowed to use certain types of materials and certain types of things. Anything that's not going to burn up in the atmosphere is a no-no. So, and I'm kind of glossing over, there's a lot of paperwork, there's a lot of certification that goes on. One of them is exactly that. So you can't use materials that are not going to burn up at the reentry. So that's number one. Number two, you have to prove that this thing is going to come out of orbit in a certain amount of time. In other words, you don't want it to be space junk. So there's a lot of stuff that goes along with that. Was that the question you're asking? Okay, yeah. So yeah, for example, stainless steel is a no-no, and things like that. So yes.
I was wondering what made your team decide on a 3x1 CubeSat instead of making, for example, like 3 1x1s to get a wider scan?
Okay, so why that form factor? Why 3x1 in that direction?
Yeah, instead of like, for example, making 3 individual smaller ones and then you can scan a wider range.
If you put, well, okay, so if you put 3 individual ones, the detector itself is about half a U, the spectrometer. Then we have to put the radios, the batteries, the everything. You wouldn't be able to fit it in that small amount. Now, if you had a bunch of these, and you're trying to say some sort of a synthetic aperture that I can make large, if that's what you're getting at, and now there's the coordination, right? And that's not trivial. So take the path of least resistance, the smallest, simplest thing we can build. And even that is a pain.
I had a question, but it was a directional one.
I was kind of weaving my way back that way, and if there's anything back there, then go for it.
Well, I had the same question as how to direction the CubeSat in that specific way. The other question I had was when you're dealing with like more deep space CubeSats, so not the ones at the U of M, but in deep space, what is the data? How does the data come back and forth?
Okay, so believe it or not, that question is the question that motivates a lot of the research I'm doing with alternate navigation systems in deep space. Currently, pretty much most spacecraft in deep space use NASA's Deep Space Network (DSN) for doing the comms. So it's a collection of 3 antennas. There's one out in California, one in Madrid, and one in Australia. Basically, they could see the entire. And so yeah, so they send data back and forth on the Deep Space Network. So, and right now navigation is also done that way. So every spacecraft that's out in deep space can't figure out where it is on its own. It has to talk back and forth with Earth to do it. So the idea of using pulsars for navigation is one of the many techniques people are looking at for being able to cut that umbilical with Earth so that spacecraft can be on their own in deep space. And the other problem with that is, right, if you're at, like, for example, New Horizons, when I was at Pluto, that was, tens of hours before you sent something and it came back to you. So you had to plan days in advance for any maneuvers you did.
So that process is usually automated, or is that usually a reaction?
What do you mean for attitude control and for again, I mean, a lot of spacecraft reaction wheels are common for attitude, but whether they're autonomous or they're being controlled, I don't know. It depends on spacecraft and spacecraft mission to mission. But again, the need for deep space navigation, autonomous navigation, is exactly that. They want to be able to have spacecraft in the future that are a lot more autonomous than they are now. Yes.
With that deep space network communication, I know it's getting really crowded. Are you being bumped into the alternate frequencies, or are you?
So we're doing research, right? And the research is motivated by the fact that the deep space network is getting oversubscribed, right? So
Yeah.
we, NASA, and others that are looking at using alternate means is exactly that, because everyone wants to talk to their spacecraft, and you have to schedule a time on the deep space network. And then not only that, right? It's when you're talking to your spacecraft on the deep space network to do a position fix, it's just not, okay, talk to it and it comes back. You have to take repeated measurements for quite a while. So yeah, with all the stuff that's out there, it's getting crowded. It's becoming, and it's expensive, by the way. It's not cheap to have to pay quite a bit to get services on DSN. Right?
Is it a constant data stream that's coming out, or is it buffered or delayed at all?
On
Or
EXACT, on our CubeSats, on the ones we're building.
yeah,
Okay, so rear, at least the way they're being designed right now is that they are going to collect data. And whenever there's an opportunity, we're using a particular radio, network of radios mostly located on the continental US and Hawaii. So whenever they are over one of these transmission stations and they find the opportunity, they'll send the data out. Otherwise, they're just going to save it on hold. So in other words, we can't really talk to them unless they're over the continental US.
about how much, I want to say hard disk space, but solid state space, I mean, storage, I guess.
It's a few gigs, but the radio data links we're using, right? So we're using the ground station, the ground station network that's run by the Aerospace Corporation, right? We have an agreement with them, we're kind of locked into their radios. But with the agreement we have, they're promising us 10 megabytes a day of data. So it's not a lot of data that's going to be coming down. So average 10 megabytes a day. Not some days will be more, some days will be less. So it's not a lot of data. So it's a trickle that's going to be coming down, and on board it's going to be a couple of gigs that we have in storage. So
And with something like that photo of Mars from a different, obviously different CubeSat, so that must have more storage capabilities or
more
something.
storage capabilities, and they've
And
got
more bandwidth.
they got more. Oh yeah, they got more bandwidth. I mean, there are radios that we could buy. I mean, the data like the radios that the Doves use. I mean, that's a ton of data they're shooting down on those. Yeah, and you just have to pay for it. It's more power. We're a university and we're on a lean budget, so we're trying to use as inexpensive things as we can. And well, it's again inexpensive in folks. So. Right, what time am I supposed to stop? 1, 2?
2 o'clock.
All right, I'll, if there aren't any more questions, I guess we are going to the exhibits downstairs. If anyone has questions about what we're doing here at the U of M with CubeSats, reach out to me. I'll be more than happy to probably bore you to death talking about this or try to answer your questions. So, all right.